Hi guys, so today I want to talk to you about how atoms form ions. Now this has to do with the electrons. So the electrons essentially in order to form an ion are going to be traded from one atom to another. And it's those outer shells of electrons that are going to be trading here. This gives them an uneven number of electrons and protons than they have in the atom, so they have a charge, and these are able to attract and repel each other. So why would atoms do this? Why would they form an ion? Why would they form this charged particle? Well, the reason why is sometimes referred to as the octet rule. Okay, what kind of goes on is atoms they don't really have desires, but they want to have their outer shells of electrons completely filled up with 8 electrons, both the s and the p, all 3 of the p's completely filled. So essentially they want to look like a noble gas. The noble gases have 8 valence electrons. All of them want to try and have 8, fill in the s's and the p's completely. They will react with another material to achieve this goal, getting 8 electrons here. Now there's 2 ways they can do it. Okay? Either they can steal a few extra electrons to get 8. This is what they're going to do if they are close to having 8. So if they have like 7, then they're going to steal 1 more, then they'll have 8. Okay? It just takes a few more to finish them out. This is what they're going to do. If they have 6, they're going to steal 2 more, and then they're going to have 8. Right? However, what if they're not even close? Let's say they only have, let's say, 1 valence electron, and they have to steal 7. Well, if that's the case, then it's not really practical for them to try and steal 7. What is more practical is for them to just get rid of that 1 electron, give it away to some other element that wants it, and then instead of having that outer shell be full, now their inner shell, that innermost shell, the one right below it, is now completely full. It was already full before. So they just give away that 1 extra electron so that now their outer shell is that inner one, and it's completely full. And it's more stable for atoms to do this. Okay, they want to do this, but the reason why is because they're more stable. So it's called the octet rule. Essentially, atoms are always trying to get an 8-electron outer shell. Either they're going to gain a few by stealing them, or they're going to give a few away so that their outer shell is empty, and then that means that their outer shell will now be the one right below it. Okay, and that's already full. So an example of a substance that is made out of ions would be sodium chloride. Okay, so sodium, which is an element that's actually highly reactive and super dangerous for human beings. Chlorine, also another element that is poisonous. I mean, if you look at these 2 elements, sodium is a metal, and it is shiny, it conducts electricity, and it reacts violently with water. We wouldn't want to put sodium in our bodies. Chlorine is highly poisonous. They actually used it it's a gas, and it's highly poisonous. They used it during World War I as a weapon. They used to drop chlorine on people and fill the area, and it would cause them to start like vomiting because they couldn't breathe right, and it just all sorts of bad things happen. So why is it that table salt, which is sodium chloride, why can we eat it? It's because they've chemically reacted, and sodium chloride, this compound, is now sodium ions and chlorine ions. So the way this works, sodium has an electron configuration of 1s2, 2s2, 2p6, 3s1. Okay, there's a total of 11 electrons here. In the outer shell, the 3rd energy level, there's only 1. It has 1 valence electron. Okay, so we would draw a Lewis dot diagram like this, with 1 dot above the sodium. Okay, so that's sodium. Chlorine. Chlorine has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p5. So this has 17 electrons total. The outer energy level here is the 3rd, and it has 7 there, 2 s's and 5 p's. Okay, so 7 valence electrons total. So it would look like this. We would have a Lewis dot diagram with 7 electrons around it. One of those is unpaired. All right? So we have these 2 elements here, sodium and chlorine, and both of them are 1 electron away from a full outer energy shell. Chlorine just needs to get 1 more. Sodium, if it loses that 1, it will then have its outer shell be the one right below it, the 2nd energy level instead of the 3rd, and so they'll both be happy with an outer energy level with 8 in it, completely full. So what's going to happen here is sodium is going to give its electron to chlorine. Okay, so the electron goes from sodium over chlorine. This means that sodium now has more protons than electrons because it lost an electron. So now there's more protons there, so it's positively charged. And chlorine, now it's got an extra electron that it didn't have before, so it has one more electron than protons, so it is negatively charged. They form ions, positive and negative ions.
When a piece of sodium metal is added to a flask of chlorine gas, a vigorous reaction takes place that releases a lot of energy, and sodium chloride, a common table salt, forms. The chemical details of sodium chloride formation are similar to the formation of many other simple ionic compounds. Let's view the process of ionic compound formation on the atomic scale. Many chemical reactions occur through a series of steps. In the process of ionic compound formation, the key step is electron transfer from the metal to nonmetal to form oppositely charged ions. As a chlorine molecule approaches the sodium surface, yet before it makes contact, electron transfer occurs. Then a series of rapid steps, too complex to detail here, forms free chloride ions that are attracted to sodium ions, and energy is released. Let's isolate the key step and examine a simplified version of it. Electron transfer from a metal atom to a non-metal atom. The sodium atom has 11 protons and 12 neutrons in its nucleus, and 11 electrons around the nucleus. The chlorine atom has 17 protons and 18 neutrons in its nucleus, and 17 electrons surround it. The sodium atom transfers an electron to the chlorine atom, and the ions attract each other and release energy. The loss of the electron converts the sodium atom into a smaller, positively charged sodium ion, Na+, while the gain of the electron converts the chlorine atom into a larger, negatively charged chloride ion, Cl-. Let's view this essential step once more. Electron transfer and ion attraction occurs countless other times between the sodium and chlorine. The large quantities of energy released vaporize tiny clusters of ions, and these attract others and release more energy. The clusters eventually aggregate and coat the walls of the flask. And even though table salt is not obtained this way, the product of this reaction consists of the same regular array of ions that makes up any sample of crystalline sodium chloride.
So next, let's talk about ionization energy. Ionization energy is the energy required to remove an electron from an atom or ion. Essentially, guys, this is the energy it takes to make a positive ion, to remove an electron. So this is only going to apply to removing electrons. Okay? Now, the lower the energy, the easier it is to remove that electron. Right? So some atoms are more likely to lose an electron than others. Now, the first electron, first ionization energy, first one it loses. What's going to happen here, it's in the outer energy level, so something like lithium and sodium, they both have one valence electron, okay, but they're different sizes. This actually has to do with the radius, with the size of the atom. So lithium has one valence electron and it's in the second energy level, whereas sodium has one valence electron and it's in the third energy level. Now, because lithium, it's in its second energy level, that electron is in the second energy level, it is actually closer to the nucleus, and so it is more tightly held on by lithium than the electron in the outer energy level in sodium. Okay, so it's the size here that matters. The more of the electrons we have separating that one electron from the center, from the nucleus, like for example, there's 2 electrons, there's 1 orbit here, and there's 2 orbits here with 10 electrons. The more things separating them, the looser that outer electron is being held. So the less energy it takes in order to remove that electron. Essentially, sodium is going to have a much easier time of losing its electron than lithium will. Okay, it decreases the energy as you go down a group. So any outer electrons, the further they get from the nucleus, the further they are from the attractive forces, and so the more loosely held they are, the less energy they require to remove. So lithium in that alkaline metals is going to be the hardest to remove that electron, but then sodium would be a little easier, and the one below it, potassium, would be even easier, and rubidium would be even easier. Cesium, it's so easy that cesium atoms are literally like, they react with almost anything that comes along, trying to get rid of that one electron. Okay, the bigger the atom gets, the more easy it is to just lose that electron, the first ionization energy. Okay, now as you go across a row, though, atoms get smaller, remember? So lithium, even though it has the same number of orbits as fluorine, lithium is a bigger atom than fluorine. Okay, so that one electron in lithium there compared to fluorine is actually held pretty loosely. It's more tight than the one below it, which has 3 orbits. But if you're comparing to everything with 2 orbits, that one electron, because it's the furthest from the nucleus, is the loosest held in its row. Okay, so anything that's smaller, okay, they get closer and closer to that nucleus, and so those electrons are held even more tightly. Hence why they actually are closer, because fluorine, more protons there, it kind of pulls all those orbits in a little. So it increases in ionization energy across a period. Those extra protons make it harder, make it take more energy to remove that electron. Okay? So let's practice for a second. Here's a periodic table. I would like to ask you, which is easier to remove an electron from? Which is easier to remove an electron from? Is it easier to remove an electron from calcium or strontium? Pause the video, get an answer. Okay, it is easier to remove an electron from strontium. This is actually lower energy to remove it, lower ionization energy, because it is a bigger atom. This has 5 energy levels, this has 4 energy levels. So the 5th energy level, since it's further from the nucleus, it will be much easier to remove an electron from it. Let's try another one. Which is easier to remove an electron from? Aluminum or sulfur? The answer is aluminum. Aluminum is easier to remove an electron from than sulfur. This is because sulfur, which has more protons, even though they both have 3 energy levels, sulfur has more protons than aluminum, so it pulls those 3 energy levels closer, and so it's holding its outer energy level tighter there for sulfur. It's smaller. Aluminum, which is bigger, same 3 energy levels, but it's not quite held as tightly for those 3 energy levels, and so this would be easier to remove that electron from. Now, the next property I want to talk about is something called electronegativity. Electronegativity is kind of the opposite of ionization energy. Electronegativity is the ability of an atom to attract electrons. Okay, ionization energy was like how easy is it to get rid of electrons. Electronegativity is like how much is it going to attract them and actually take electrons. Okay, now the most electronegative atom on the periodic table, this is actually something we can measure, electronegativity, it's been measured before, is actually fluorine. All right? Fluorine is the most electronegative one, this blue one here. The least electronegative one is the one that's easiest to remove electrons from, francium. So francium is actually the easiest to remove electrons from, so because of that, it is the least likely to attract any electrons, because it wants to get rid of them. So fluorine, though, it's holding on to its electrons really, really tightly, because it's small, it's got lots of protons there, it's only got 2 orbits, so it pulls those electrons in really, really closely, and because it holds on them so tightly, like we talked about with the ionization energy, it attracts electrons as well. So fluorine is actually the element that is most likely to steal an electron. In fact, fluorine doesn't exist by itself in nature because it pretty much steals an electron from anything it comes across. Okay? Now, oxygen, nitrogen, and carbon, since they are a little bit bigger, I know it's kind of opposite here, but there's less protons there, so they're a little bit bigger with the same 2 energy levels. So they attract electrons a little bit less than fluorine does. And as you go down, they get more and more orbits, so those get bigger as well, and so those attract a little bit less. Now, you may also notice in this chart here that the noble gases, except for these two, are gray. That's because this is about attracting electrons, and the one family that already has 8 electrons in its outer shell is the noble gases. So the noble gases don't react with anything, which means they don't want to attract, they don't want to get rid of any electrons. Like, they hold them really, really tight, but because they're already perfect with 8, they don't attract any. So this whole family, with the exception of these two right here, we have been able to get them to react occasionally, so they do have a little bit of an ability to attract extra electrons. This whole family is unreactive, and so we can't actually measure their attractiveness for electrons because they essentially don't have an attractiveness to electrons. Okay, so the pattern here, electronegativity, how much it attracts electrons, increases as you get closer and closer to fluorine. Okay, fluorine right here, not to the noble gases though. And it decreases as it gets bigger. So as you go down in a family, it gets less and less attractive to electrons. Let's practice again. Okay, I'm going to name 2, and I want you to know which one is more likely to attract electrons. So the 2 I'm going to give you, sulfur and selenium. Which one attracts electrons more? Okay, out of sulfur and selenium, sulfur attracts electrons more because it has 3 energy levels, whereas selenium has 4 energy levels. So 3 energy levels means that the electrons would be closer to that nucleus, and so sulfur would attract electrons more than selenium would. Let's try another one. Okay, which one would attract electrons more? Bromine or arsenic? Bromine or arsenic? So out of those two, bromine and arsenic, bromine would attract electrons more. They are in the same row, which means they both have their outer shell being 4. So it's not that they have more shells or less shells. Bromine is a smaller atom, though, because it has more protons. It pulls the same number of shells in a little tighter. And so bromine, since it's slightly smaller and it's a little bit closer to the nucleus, will be able to attract electrons a bit more than the slightly larger arsenic. Okay? Now, electronegativity and ionization energy, this idea of attracting electrons and getting rid of electrons, essentially, even though some things are more likely to get rid of electrons than others, and some things are more likely to attract electrons than others, they can be put into 2 categories. It's basically these things give electrons away, and these things steal electrons. We call those metals and nonmetals, right? So the periodic table can be broken essentially into these 2 sections. Everything that is very likely to give away electrons, because it's low energy to actually give it away, we call a metal, and that would be everything essentially from francium, the alkali metals, all the way over to like aluminum and down here. You might notice that this line here separating them is a little weird. That's because it gets more and more likely for you to lose those electrons as you get bigger and bigger, and so we can actually have more of them in this bottom row than we can in this top row here. Okay. Now the nonmetals, the ones that attract electrons, they're going to try to steal them. That would be the ones over here. All right. Top of the periodic table has more nonmetals than the bottom, and as you get over to the right, you get more of them as well. Okay. So this is the nonmetal section. Now, there is sort of an in-between. Everything here in green is considered what's called a metalloid. Those are the ones that kind of have like an in-between ionization energy, in-between electronegativity. They're kind of like right in the middle where they can essentially go either way. They could steal electrons or they could gain them. So they basically have properties of both here, metal and non-metal. So this is kind of like the in-between section. Most of the elements we can either label, yeah, they're going to lose electrons, or yeah, they're going to steal electrons. These are the ones where it's like, maybe. So they're kind of like this in-between here area. Okay, so going back to that salt, sodium was a metal. Okay, it's over there on the metal side. Chlorine is a non-metal. Right? It's over on the nonmetal side of that separation. So a metal, low ionization energy, it's going to lose electrons, which we saw. Chlorine, a nonmetal, it's going to have high electronegativity. It means it likes electrons, so it's going to try to steal some. Okay, so back to what happened. That one electron from sodium was stolen by chlorine, forming the two ions. All right, positive and negative. Now, there are two types of ions. We have the cation. Cation is how you say that. The cation is the one that loses the electrons, and so it's going to have the positive charge. So this would be the sodium in this case. The sodium with a +1 charge. It lost an electron. That's the cation. Anion, that's the nonmetal one. That's the one that's going to gain the electrons, and it's going to have a negative charge because it's got extra electrons. So in this case, for the sodium chloride, it'd be the chlorine. Chlorine gained an electron, and now it's negatively charged. So two names here for them, cation and anion. Okay, and this is actually where you get the name cathode and anode on a battery, by the way. Positive and negative end. Cathode is the positive, by the way. Now, when you have positive and negative ions, they attract each other. Okay, when you have cations and anions, they attract each other. They need each other to kind of form because one steals the electron from the other. But once they're formed, the positive and the negative are attracted, and so they actually form sort of like this crystal patterned lattice. Okay, this is actually what sodium chloride looks like. Because the positive and negatives attract each other, this positive here, the smaller one, attracts a bunch of negatives that stick to it, and then each negative attracts a bunch of positives that stick to it. So the positives are all surrounded by negatives, and the negatives are all surrounded by positives, and so you get this repeating pattern of positive, negative, positive, negative, positive, negative. Now the formula for sodium chloride, NaCl, essentially just breaks it down into what one unit in this repeating pattern is. So one unit would be a chlorine and a sodium pairing up together, sticking to each other. So this is sort of what we call the formula unit or the formula of sodium chloride. It's just what is the repeating unit here. It's 1-to-1. Okay, everything is 1-to-1. So there's a lot of patterns that can form when you have ions depending on the two charges. If it's a positive one and a negative one, you get 1-to-1. But what if it's like a positive 2, where you lost 2 electrons, and like a negative 1, or you have maybe a negative 3 to a positive 1, right? So there's lots of ways that this can form. And when we have these different charges, positive and negative, we actually get several different repeating patterns. So it's just a repeating pattern of 1-to-1 for what I showed you. But then if you have like one of them being 1 and the other one positively 2 charged, then you'd get this like double pattern where you have more of the 1s than you do of the 2s here, the positive 2s. Okay, this would be a 1-to-3 pattern, meaning you had like a positive 1 and a negative 3, or a negative 1 and a positive 3. That could go either way. And this would be a 2-to-3 pattern. Okay, 2-to-3 is kind of a tricky one to form in your mind, but it's a repeating pattern over and over again. Now, drawing Lewis dot structures for this. Okay, drawing the Lewis dot structures for this can be a little tricky. So I've already done one of them, but let me just kind of walk through it again. So we had the sodium with 1, chlorine with 7. Okay, during the formation of this ion, one of those goes over to the chlorine from the sodium. So the metal loses its electron, goes to the chlorine. Okay, writing the formula for this. First off, the sodium now doesn't have an electron, but it also has a positive charge. So we're going to draw the sodium atom now, but now it doesn't have any valence electrons around it because it lost the 1 valence that it had. We're not going to draw it with 8, even though it's now got 8 in its inner shell here, because it's more practical for us to see that it lost its 1 than it does to see that it now has its inner 8. So no valence electrons around it now is kind of how we're going to draw it. And we're also going to give it a charge. We're going to put brackets around it and put a +1 there. The chlorine, it now has 8. Okay, it gained that 1. We're going to put brackets around the chlorine and put a little negative charge there. Okay, so the charge of that cation, the positive one, represents how many electrons it lost. And the charge of the anion, the negative one, represents how many electrons it gained. All right? Now that's one example. Let me show you another one. Magnesium fluoride. Okay, this is actually a 1-to-2 ratio. Right, so if we start with magnesium, it's going to take 2 fluorines in order to actually react with it, because magnesium has 2 valence electrons and it's going to try to get rid of both of them. Fluorine has 7 valence electrons. It's going to take 1 for each. So since magnesium has to get rid of 2, it's going to have to give 1 to each fluorine, right? So 1 goes to each fluorine. So what do we have after this reaction? First off, we now have a magnesium with no valence electrons, and it has a positive 2 charge. Okay, so put brackets around it. Now it's got a positive 2. Then each of the 2 fluorines now have 8 valence electrons around them. Okay, they have that extra one now, went from 7 to 8, and put bracket around it. They each have a negative 1 charge. Right, now it takes 2 of them because the magnesium's giving away 2. Okay, so 1 has to go to 1, 1 goes to the other, and we have 2 different charges on the magnesium and the fluorine, positive 2 and a negative 1. All right, and that is how you draw ions, draw the Lewis dot structures for these ions. That's it for today.